Should I just start?
Yeah, no, go ahead.
Hey, so I'm going to give a very high-level overview just to kind of calibrate. I know we kind of have already a few discussions about the conjecture and correlated agreement and the mutual agreement. Giacomo gave what we said yesterday and discussed today. This is another overview with a bit of a personal history. At the end, we're going to see kind of the formal definition, a few numbers, and feel free to ask questions. It should be kind of a short document, something long, so you can ask questions. Okay, so just to set up some notation, we're talking about read-solving codes. Okay, so we're going to have some function f. We're going to have the evaluation of the function. Okay, on some domain. So in every element here, the domain is kind of 1 to 3 up to 16. Okay, we just write the evaluation of the function on that element. What is a read-solving code? It has some parameters. We have the field that we fix, the evaluation domain, okay, and the rate of the code, which is d over n, the degree of the polynomial, okay, over the size of the domain n. Okay. When the domain is bigger, then the rate becomes smaller. You have more redundancy, but that makes it better for the verifier because it's easier for him to catch bugs. So I never know if a smaller rate is good or bad. Okay, for coding people, like a small rate is bad because it's more redundancy. For crypto people, like okay, it's good. You have less queries, right? So yeah. So in steer is like improving rate, right? Shift to improve rate, and this improve. Okay, coding people told me that you're not improving the rate, you're making it worse. Okay, so it depends how.
Better for the verifier, worse for the prover, basically.
Yeah, it's good, better for the verifier, worse for the prover. Yeah. Okay, good. Okay, so some of these slides were made by my student Gal, and then later we have some slides made by Giacomo, or at least some variants of these slides. Okay, so we have our function f, we have the evaluation domain L. Okay, and now we have in green, this is kind of the part that agrees with some code word. So f is an arbitrary function, doesn't have to be a code word. Okay, a code word is going to be when f is actually a loaded function, but f could just be close to a loaded function. For close, I mean, for example, here the green part agrees with some polynomial. The non-green part does not agree, okay? And then this delta is the distance from the code, okay? And in general, the distance is the distance to the closest polynomial, okay? So the distance could be small, the distance could be big, okay? Actually, in general, we're thinking like in the previous session, when we took f of x minus beta over x, right? So if f doesn't equal beta on 0, then this quotient is actually going to be very far from valid code. Okay, so it's going to look more like this. Okay. Well, if it was half, then the green part will be like half. Okay. Was there a question? Okay. So now we're going to continue. We're going to have mostly green kind of notation, but in general, okay, what you should think in your mind is that one function f could be close to many different polynomials. Okay, so now we see kind of different colors, and each one is a different polynomial that is close to on a different region. And even this drawing is not truthful because actually the places that it's close to different polynomials could intersect. Okay, so this is just a simplicity of drawing, okay, but they actually intersect, and it could be like intersect with many different polynomials, and that's actually what makes things kind of much harder. Okay, so the drawings for now are gonna be in the unique decoding radius, so we're gonna have one green area, but you always should think in your mind that we have many of these different green areas with different colors. Okay. So what is correlated agreement? So now I have many functions here, kind of the notation changed to C, but the C is the same F, okay? Just because we're thinking of them as columns or some other thing, but for now it doesn't really matter. we have many functions. We never want to low degree test one function, right? What do? We want to batch them together. Okay, great. So we're going to take a random linear combination of all these functions. We create this C star, which is a random linear combination, and then we're going to, just test C star. Okay. So we need some promise on. Let's say we tested C star and we found out that C star is very close to low degree. What does it tell me about all the CIs? Right, this is kind of the basic question we're asking, and this is exactly what the proximity gaps gives us. And this is a theorem by, okay, anybody remember the authors? Okay, so I don't forget.
Bensason, Karman, Ishai, Koparty, Saraf, yes.
Saraf, yeah. Okay, great. Thanks. So this theorem actually started this kind of agreements. I think already go back to GDW. So this is Rothblum, Badan, Wigderson, where they kind of had this initial result, but okay, we're talking on this formulation. So they're saying if, okay, with high probability, C star is going to be close to Ritz Solomon. Okay, so just before I continue. Obviously, I cannot say anything worst case, like maybe all the alphas are 0, and then C star is just a 0, okay? Like regardless of the CI, it could be that C star is close to the loop, okay? Kind of have to say something probabilistic here. I want to say, if the probability over the alphas that C star is close to low degree is bigger than some errors, than some small error epsilon, okay? And we're going to see exactly what is epsilon. Currently just, something nominal in D and or F. Then it means that for every J, every Cj is close, okay? And actually it's very important here, it's the same distance parameter, okay? It's mu, whatever this letter is. Okay, so it kind of, the GVW theorem kind of had this, and here it was kind of mu over 2. So they lost something. And this loss for phi would be very bad. Because you have like many steps, you're going to lose each time another factor of 2.
Just a very strong question about this statement. We're checking over all possible alphas. So is it really helpful to look at this as a probabilistic statement, or just accounting like the set of alphas that
Yeah, it's
cause...
accounting. It's the same. You just want to say that the number of alphas that make this close is, if it's large enough, then it means that all of them are close.
Just in terms of like notation, or even in how we describe the statement, is it helpful to have it as a probability, or just like size of set?
Look, eventually it's a...
Like they mean to
Well,
say...
the verified
like,
loss, so
I
you
think
do think of it as
probability does become helpful for higher dimensional statements when
Okay.
you're quantifying over not just a one-dimensional parameter, but like something bigger. Then if you talk about count, you have a kind of q to the n-1 factor. In other words, the expression looks more convenient when it's about probability, because then you just have one q in the denominator, and instead of, if like, let's say, I don't know, k is a dimension of the challenge space, something like epsilon over q looks nicer than q to the k minus 1.
In short, probability is a normalized thing,
Yeah.
so it's always easier to look at something normalized. I don't know where the alpha is coming from. Is it one alpha here? It's kind of L alphas, right? So counting is always kind of hard.
I'm asking because I've seen a lot of people confused by the statement. Like, you have this if-then property, and the if is conditioned on a probability being higher than something, and I can see how that might confuse you.
Yeah, so in the proofs many times you just say, oh, let's define a set of all alphas, and we actually, but for the definition we look at probability.
Would it be interesting to accept some kind of distance degradation in order to get a better epsilon?
Okay, that's an excellent question. So as I said, they started out with a distance degradation, okay, by a factor of 2, and their error actually was much better. Okay, that was fine for the GVW application. For Fry and Steer and Weir, I think like that wouldn't be so good. Maybe if you have think if you negate by a factor of 2, that means like much more queries. I don't know if it's worth it. If you have a additive loss here, minus something, I think that would be fine. Okay, fine. So you lose a bit in the distance, like 0.1 or 0.01, and maybe using that you can make the error go down, and then you can use a smaller field. Actually, that would be amazing.
Yeah, I think that when you do like the word proof, even if you lose a bit, since you are in the way of course switching to something with new or fresh distance, you're probably kind of fine. So this is something that you can try to do to reduce the error, but you have to analyze and figure out what's right here.
No, you're right. But even in weird, if you lose a factor of 2, I think you will.
No, 2 is too bad. 2 is too bad.
Yeah.
You have 200 queries instead of 100 is bad.
Is there any intuition what happens with this thing when we adjust mu or epsilon? Like when it's like, what happens at the edge?
So this should be, okay, so this theorem is true for all mu in some regime. Okay, obviously up to Johnson-Bauer capacity. I'm going to get to the regime in a second. But inside the regime that the theorem is true, like you're asking if epsilon changes.
Yeah, does it become trivial at some point when we modify epsilon?
I don't think it becomes if we modify epsilon.
Like
If you modify mu, like
If you modify mu to the unique decoding radius, then it's an easier proof. It's still not easy.
So how do I understand this? How do I understand this? When we kind of make mu small, it means that we claim that the result is very, very close to somewhere. Right?
Yeah, but you start with something that is mu close, you end with something that is mu close. So the two statements for one mu and a big mu and a small mu, they're incomparable statements.
Yeah, and
You,
for
you
small
end
mu,
with something stronger, but you start with something stronger.
yeah, and for small mu it means like if you appear very, very close, it means that your inputs were also very, very close. That means for small mu. And big epsilon means that for like big noticeable fraction of alpha you don't appear anywhere.
Yeah, big epsilon means that you might have a good chance of this thing being close, or maybe even a code word, even though the CIs will not be code.
looking back at the system, right, the epsilon will return exactly the soundness error, while the mu is the number of queries. And typically it turns out when mu is like close to 0, the closer you go to 0, the easier the thing is to prove. When mu is larger, things become harder to prove.
When you fix it for the same epsilon.
Well, usually like you get like worse epsilon. The way you prove these things, you find a mu that you care about, then you do the proof, and that gives an epsilon. So typically what happens is that the more mu grows, the larger epsilon grows, so the error becomes worse. So for example, like in unique decoding, the error is kind of like n over s. In Johnson-Bound, it's something like n squared over s plus some other awful terms, and then up to capacity we don't know, but of course, if epsilon is 1, everything is trivial. But
how to understand this when you say when mu grows, epsilon grows? What does it mean? It means like when mu grows, you cannot state your theorem for smaller epsilon anymore. You can only state it for much bigger epsilon.
So this is stated like for any mu in a regime, you have this epsilon. Okay, so I'm not sure about like if you fix a particular mu, maybe you get some epsilon that kind of an epsilon of mu that is slightly better. I don't know of such a result. Like this
Maybe it helps. At least for me, it helps a lot at the beginning when I'm coming from the polynomial world, and read Solomon what like 2.5 years ago, and it helped me. So as a poly IOP, an equivalent statement would be if a random linear combination of connected polynomials is of certain low degree, then the same holds for each of it. And the proof is actually in the polynomial IOP model quite trivial, because if one of those initial one wouldn't speak of that load same degree bound, there is a coefficient which is non-zero for a higher monomial, and you can easily argue by a Schwarz-Zippel and get something like 1 over f.
Yeah, but it's a simpler statement because
Yeah.
the statement doesn't involve quanters.
And
Here we have
the thing is now that we restrict not to Schwarz-Zippel over the field, we commit on something a quite small domain. The thing gets much more subtle in testing things. So first of all, you can never assure that 100% of the community is plotted. It is a polynomial, you're only proximity, first of all. And second, it's kind of hard to even quantify, knowing that you're never sure you have a polynomial. Yeah? It's kind of hard to quantify what can all happen just taking this random linear combination. I don't know, this was no explanation, but maybe the direction helps.
This is what Correlated is saying, like if I take a random linear combination of actual polynomials, okay, then the probability that the monomial with the highest power is cancelled out is 1 over f. Okay, and if that happens, I actually get a lower degree polynomial. That's very easy to prove.
Exactly.
Here it's harder because you're saying, okay, the C star agrees on these 3 locations, right? Now I want to show that all the CIs also agree on some 3 locations. I don't want even the event that C star agrees on 4 locations. Like I don't want even it be slightly, like even 1 field element closer to the degree.
Well, that would be fine later.
I was thinking that
You're jumping ahead. Okay? You're jumping ahead. Okay?
So if I may say this again, when you say like when mu grows, epsilon grows, you sort of say that when mu grows, it's not enough to have just a handful of alphas for which this closeness holds. You have to collect more alphas, and only after you collect sufficient many alphas, it means for bigger epsilon you have to have more alphas. When you have more alphas, then it starts being true that the inputs are also closed.
Yeah.
But if maybe for some, just if you collect just a few alphas, doesn't mean it.
Okay, so this is the original statement. This only tells me that taking random linear combination preserves the distance. Okay, I had things that had some distance mu, and the random linear combination also has the same distance. In this paper, they actually proved a stronger property called correlated agreement. Okay, a strictly stronger property. Turns out to be very, very useful. Actually, we use it in many places, not only kind of in batching and low degree testing. Okay, yeah, obviously you can batch and only test C star. Okay, so what it showed is that all the CJs, like this cannot be the picture. This is not reality. This is not what happens when you take a random linear combination of things. If you take a random linear combination of these things, actually you will get something that's very, very far. Okay, C star will be very, very far. What actually you can prove is that if C star looks like this, then what they showed that all the CJs have correlated agreement. Not only that they're mu close to low degree, they're mu close to low degree on the same set of elements, on the same subset of our relation domain. So, okay, so the picture actually looks like this. Okay, and all the CJs kind of correlated somewhere. Okay.
Is the statement some kind of symmetrical with respect of all these parameters? You can swap C star with C1.
No, C star depends on C1, right? There's no swapping. C1 up to CN are fixed, and C star is a function of alpha, right?
That you can divide by alpha and like rearrange.
No, I don't know what that means.
So you think if I like have C1, C2 and C1 plus alpha C2, then if I know something about C1 plus alpha C2, this also tells me something about C1 and C2. I can think of C2 as like C1 plus alpha C2 minus C2 or whatever. Or divided by the alpha.
It you look at the statement, basically C star is just a linear combination, and you can select any of its linear combination because any of those is a linear combination of everything else with the same amount of parameters.
Okay. I'm not sure I follow that.
There is
Yeah, the question is how many alphas can you choose?
You can write C1 as a linear combination of C star and C2 of CCL, and then maybe apply the same result to get mutual correlated.
But C star is not defined. We don't have C star. After we chose alpha, we have C star. Now we want to claim something, so I don't know what it means to kind of reverse order. The reverse order now what I choose, but a new alpha, like what is it?
And I guess there is no precise rules on the position of the green squares. So, like, they can be anywhere.
They can be anywhere, yeah. Okay. But
maybe
before we
C star is a linear space, right? So you can view it as a linear space. And then we can say, like, if we have a linear space and the big fraction of this linear space is enclosed, then any basis point, any set of basis point, any basis point actually is closed.
Yeah. Okay, so now we have this picture, okay? Before I continue into mutual agreement, this cannot be the picture. This is a false picture. Okay? Okay, good. If I have correlated agreement on some domain, then on this domain, a random linear combination of polynomials is obviously a polynomial. Okay? That's true for any alpha, right? With probability 1. Okay, it doesn't matter. So obviously, I should have the correlated agreement down here. Okay? However, remember, we're not in the unique decoding radius. I can have many green areas. Okay? So nobody said that C star, okay, so think fine, I have a green area down below. But it could be that C star has another green area. Okay? Nobody that says that any time C star has a green area, then the CIs also have the same green area. Okay? So actually this started actually in ACY. Okay, this is a paper kind of already 2 years ago. What we had there is we kind of thought that what we have is a mutual correlated agreement, and then during the proof we kind of realized that we actually don't have mutual correlated agreement. So what is mutual correlated agreement? So we did in ACY, we kind of conjectured. We didn't really conjecture it back then. Back then we kind of just modified the protocol not to work with mutual agreement. It wasn't a practical scheme, so we kind of didn't care of having a big cost. But what we conjectured that not only the CJs, but also C star itself, all of them should have correlated agreement. Okay? What it means is that the picture looks like this. Okay? In the unique decoding radius, it should look like this. In the least decoding radius, it looks like this for every color. The greens are correlated, the purples are correlated. Okay? Any place that C star is close to the degree, all the CIs are close to the degree at the same place. C star in general is going to be close to the degree in many different places. Okay? And each and every one of them implies that all the CIs are close to the degree at the same domain. Okay? So this is mutual correlated agreement. With high probability over alpha, okay, except for some error, all the CIs and C star are going to have correlated agreement.
Excuse me, is the error, is it the same for all the kinds of agreements that we talked about?
We'll see. Currently it's a conjecture, right? So, yeah, conjecture is the same error. Okay? Well, at the time of this talk, it's a conjecture, and we'll get into it in a second. But okay, so in ACY, we kind of encountered this problem. We didn't know what to do. We just changed the whole analysis to not have a correlated agreement. But every time I give a talk about it, I'm saying like, look, let's look at a simpler version of the protocol. We'll just assume this conjecture, and actually the protocol just doesn't use it. Okay. Later on, it turns out that this property is actually very useful in practice, and that's why we actually wanted to conjecture it, and then started proving it. Okay. So before I continue, I just wanted to show you that you can just see from the picture that this conjecture is true for the unique decoding radius. Okay? What do I mean true? I mean that it follows from the standard theorem that the CIs have correlated agreement. Why? Assume that CI has a correlated agreement. We're in the unique decoding radius, so there's only one green area. Then we know that if all of them have correlated agreement, C star must have correlated agreement down below, right, wherever the green is. And if he has correlated agreement here, he cannot have another one. Okay, he cannot have two because we're in the unique decoding radius, and the distance of C star is going to be the same distance, okay, by the same theorem. So C star is also going to be the unique decoding radius. So in the unique decoding radius, we have only one, okay, so it's really like if and only if. So this has to be the picture, okay? Well, this thing, it doesn't work is in the least decoding radius, okay? I don't know that somehow C star, you know, by taking random linear combination, kind of invented a new domain where it's close to a degree, where the CIs are not close, okay? That's kind of not promised by correlation.
When we put something in the correlated agreement regime and mutual correlated agreement regime, do we use like the same kind of technique, for example, from the proximity gap stuff? Is it the same kind of techniques to demonstrate things in the correlated agreement and mutual correlated agreement?
Okay, that's a good question for people that actually prove mutual agreement. Maybe you guys can tell more. I stopped by conjecturing it and kind of yeah. So I put some students to read this paper and explain the proof to me, and they never came back. So in the unique decoding radius, I understand the proof, and I think actually with the student we wrote down like a proof that's much simpler and kind of half the length, okay, for unique decoding. For the list decoding, I kind of half understand the proof, not fully, and yeah, I don't know. I asked Dan Calmon and Eddie like, okay, just go over the proof, tell me if it also satisfies the mutual correlated agreement, and I'll just, you know, cite it in my paper, and that's it, like product indication. And they're like, yeah, obviously, because no, but yeah, but no, but, and then I don't know, life went on, and I didn't get like they said probably, but not
With high probability.
with high probability. But I wanted them to like sit down and do it, and I think it's a bit delicate. So yeah, but luckily we have amazing people that actually sit down and prove stuff. We'll see it in a second. And let's look at okay. So I just wanted to show the formal statement. If you look at the real paper and you see this definition, okay, so we can kind of go over it. Okay, so we have a linear code. We have some gen, which is a proximity generator. Forget about this. This is just the thing that samples the alphas, okay? Sometimes you just sample random alphas. Sometimes alpha j is going to be some alpha to the j, okay? So you kind of abstract this away with some generator, but let's forget about that. So we say that it has mutual correlated agreement with proximity bound B star. This is kind of up to what distance you can do. Okay, Johnson capacity, so it's some B star. Okay, and you get some error. Okay, this is our epsilon. Again, in the paper we kind of have many epsilons, so we cannot just call it epsilon. Okay, if for every n volts, okay, that we take, and for every distance that it's between 1 and between 0 and 1 minus B star, okay, so think 1 minus square root rho and minus rho, depending if we do. Okay, so the following holds. What is the following? Okay, so the probability that something holds is small. Okay, so we have a small error of something holding. So the probability that, notice that there exists a set S. S is the set, the three dots, the three green places, okay? The place that we're going to have correlated agreement. So with high probability, we're not going to have any set S, okay? of the appropriate size. Okay, obviously we're looking at some size. Okay, this is the distance. Okay, such that what? Such that there exists a code word in the code. Okay, so actually actual polynomial. Such that if you look at this polynomial restricted to S, okay, only at the S part, it's gonna equal the random linear combination of the FJs. Okay, so this means that the C star is close to low degree on S. Okay. However, there exists at least one of them, okay, that this one doesn't agree with any code word you find on this. Okay?
That's why
So this means we do not have we don't have mutual agreement on S, and the statement says that there's not going to exist such an S of the appropriate size.
So, some intuition would go.
Yeah, so restating in a counting argument, the way I usually say it is like the number of challenges that create agreement domains is small.
What is the agreement domain?
This green stuff. So the
number
number of
of challenges
challenges
that
that
create a
make
new agreement domain.
exactly the number of challenges that make the right hand side of the drawing have more green squares than the left hand side is small.
More.
More colors.
So maybe one thing that I first found confusing when I first saw this is a bit of the notation here, because S is a set, but U of S is treated as a vector here.
So U of S is kind of so S.
So U of
S is, for example, these three locations.
right, but in
And U
an
of S
ordered
is
way,
the
right?
restriction of U to these locations.
But it's in an ordered, it's ordered, right?
It's
So if this U of S equals sum of something, if the left is 1, 2, 3 and the right is 3, 2, 1, they are not equal, but S is a set, so it doesn't have an order. So that is what confused me first.
okay, so
I
S
think-
is fine. S is kind of an ordered set.
Yeah,
Right?
so I think it's some.
I can take the blame or blame Giacomo. So it's
I'm sorry.
not listening, so I'm gonna.
I was just going to point out the same thing that Benedict did. Is there a way of rephrasing this? Because when you ask about probability, you care about random variables or functions of random variables. But now you're stating a probability about the existence of a set. So for me, it's kind of alien to look at it that way. And have you ever thought of rewriting this?
So, I did think of rewriting this, and then I did, and this is the result.
Okay.
Every time you get the same, but
So again, this is a random variable, right? So this thing is a random variable. Okay? So we have the inputs to the thing that these are fixed. Okay? This is the random variable. And then we're kind of saying, what is the probability that this entire predicate of this random variable is satisfied? And it's a strong statement because it says the probability that there exists a set, right? And just to make sure, you cannot union bound. You cannot say, okay, let's fix the set outside and then just union bound over all sets, okay? Then you would lose kind of the size of S choose N, okay, which is a huge factor.
I think there's maybe a way that maybe for some people it would be simpler if you write it the opposite, like the counter event. You say, and then you write the counter event
You can
with
write
the
a counter
implications.
event. Look, my recommendation in general, okay, in a crypto paper, you always upper bound errors.
Sure.
Okay, once you start lower bounding good events,
Don't do that.
But
you
no,
cannot.
but I mean the thing that you visualized is the counter event, right?
Yeah. Right.
Right.
What is a hash function? The probability that you find a collision is small. Okay, it means that most adversaries with high probability won't find a collision. I never state it like this. Right? I state the bad event. But in your mind, you also think this is the bad event. So what is the good event? With most probability, like no such sets is going to exist, meaning all sets are going to satisfy both equations.
Right. But for the counter event, you can actually write it as an implication, right? And that may be
Yeah, it's
that
an if
closer
and
to
only
the
if.
correlated.
It's an if and only if. Right? It's an if and only if. It's like every set that satisfies one satisfies the other. So it's an if and only if. I agree. Because we know that if you satisfy the left side, it satisfies the right side. And this just says that if you satisfy the right side, it satisfies the left side. So together you actually get the if and only. Okay. Yeah.
Say that's for
So you can say, in other words, because I also, in the beginning, I recall that it was tough to parse the definition in the word paper. So it's like with small. So the bad event would be to find a set S over which the random linear combination coincides with the current cohort, but that set is not a set of correlated agreement. Because it was for me hard to parse the third line.
The bad event is the
Third line, sum if I doesn't agree with the code on S.
Yeah, I don't know. The intuition is on top. You see the right squares, the green squares on the right, and you look at them, and what you want is that if you see a green square on the right, that means there are green squares on the left.
Yes.
The statement says if you see a green square on the right, the probability there will be no green square in some of the columns on the left is low. Yeah?
And the probability that there will be orange squares on the left but not on the right is also low, right? You need to consider other agreement sets S.
Yes, so it's the
Additional-
probability that you exist in S. So
Yes,
that's
any color.
open.
Every color on the right is also on the left.
Exactly.
Yeah. Okay, yeah, you need to add more colors.
Any set that satisfies this, any color on the right, any set that satisfies this is also on the left.
in the same position.
Exactly. I think this formulation is kind of nice up to maybe these are not, this is an ordered set and then, okay, up to kind of this mathematical notation.
Previously, have you ever thought of thinking of this problem as a bolt and earn problem? Like throwing balls and letting them fall in urns?
Look, it is similar in many cases. I actually worked very hard to prove that kind of correlated and mutual are the same, and then you kind of go into all these probability counts. And I actually can prove it in some cases with a worse epsilon, but like you're saying, okay, fine. But essentially, because of this strong requirement that you want for there's no S, then it's very hard. You cannot union bound. You don't know. You cannot fix S. If you fix S, then you're saying, okay, you can union bound over any other point to somehow be attached to S. Okay, like some S, and what's the probability that C star on some other point, is going to be the exact polynomial that S on C star is defined. That is small, and you can union bound over n. Fine, you pay a factor of n, but that is kind of if S is fixed. Okay, and the hard part is here is S is not fixed. Okay. Good. So we started by just conjecturing. Okay. So we said that mutual correlated agreement up to Johnson bound would have the same bound as the provable bound of mutual agreement. Okay. Of correlated agreement. So for correlated agreement, the bound is proven, and this one is conjectured. Here, at that point of time, both of them were conjectures. Okay, just two types of conjecture. Okay. Again, for the unique decoding, like you can prove it easily. Okay. Okay. This is a more recent state of affairs, and maybe you can help me with citing the right people that prove this. So up to unique decoding. Okay, we know that this is correlated agreement and mutual agreement, and both have the smallest error, n over f. Okay, and n over f is almost tight. Actually, the tight bound is mu times n over f. This is actually tight. Okay, if you forget about this mu, if you think of it as just a constant, then this is actually tight.
What is mu?
Distance.
The distance, like delta.
So there is delta on the left side and eta on the right side. How do they?
Wait, so I'm in the unique decoding. Okay, I'm in the first column. You're asking about the second column?
I mean, I said epsilon is a function of delta is. There is correct, but there is no delta on the right side.
Yeah, because so I said epsilon of delta is n over f. It's for any delta in the unique decoding radius. So it just ignores delta, but it has some bound on delta.
That's the bound of delta.
Okay, that's the bound on delta, 1 minus 4 del 2. Okay, so I said if you want to be slightly more precise, you can actually put in delta inside this expression. Okay?
I think n over f can be attained exactly, right?
So I think almost like I think delta n over f can be attained.
I think
Or minus
I
like,
think you
I
can
don't
attain
remember.
that.
It's something close to n over f.
we'll talk after.
But yeah, that's very small because it's not like the problem. So in decoding, you have n over f, you can pull both of them.
And the fact that the odds are the same in both the correlated agreement and mutual theorem, is it proven or conjecture?
So in general, in the general statement, I don't know anything here. Mutual, you are correlated, they might have different errors. It happens to be that we can put both with the same error. Okay, it happens to be like maybe it hints that they're equivalent. Okay, but I don't know how to show generically that they're equivalent. Okay, it just happened to be that I know how to prove correlated agreement with n over f. You look at the proof and kind of say, oh, the same proof, almost the same proof, also proves mutual with the same error. Okay, and the attacks are the same attack, and then it's kind of the best attack, and you can match it. Then you have what's called the name that I don't like so much, 1.5 Johnson bound and the Johnson bound. Okay, so for both of them, now we know that they have the same error. Okay, so mutual. So what was conjecture in the previous slide is now actually a theorem. So Ulrich, this is a U, or I don't remember now.
Yeah, the Johnson vessel.
The 1.5 Johnson is who?
Is deep fry, JKL, and LS.
And the Johnson?
Well, deep fry was not mutual at the time, right? Deep fry did the 1.5 Johnson, the original 1.5 Johnson proof.
This the original for mutual, you say?
For just correlated, deep fry did the first 1.5 Johnson, and I think at the time they did
That was
compare-
the deep fry paper. Right?
Yeah, deep fry, I'm saying, did the original 1.5, then ADAS and GKL, they did
The global analysis, right? I never recall the names. Chinese team.
Yeah, GKL.
Yeah,
Gao.
and then this one, the Johnson bound?
The one in correlated agreement is proximity gaps, so BCIKS, and the neutral is Ulrich.
Okay. So why didn't you
I didn't know what was the
You're not
question.
sure it's an alter ego? It's not. So currently, what we know is up to the Johnson bound. Okay, we actually have an exact same error in both cases. This is, a coincidence. Okay, I kind of think it's not a coincidence. They look. I find it hard to believe that we'll have one and not the other. They look like very tightly together, but we don't have this generic proof that one implies the other. Okay, obviously mutual implies correlated, but not vice versa. Okay. Yeah.
If I understood correctly, like the 1.5 Johnson is for more generic code than read-through code, and this.
You're right. So this the Johnson bound is for Reed Solomon. The 1.5 is for any linear code, right? And do we have something for MDS codes generically for mutual?
I don't think so.
I don't think we have something better than the 1.5 Johnson.
And the N on F is also just Reed Solomon, I think. The unique decoding is also, I think, just Reed Solomon.
Yeah, because
The unique decoding is also Reed Solomon. Right.
Yeah, because with the other one,
Right, that's right. So what I wanted to say is that sometimes N over F is very nice, but then you can take a smaller field. Okay? I mean, you go to the listening coding, you have like bigger errors. I want to point out slightly, not relevant to now, to this talk, but you can always do grinding, not only for the query phase, but for all the rounds of the protocol. So even if you have a round in phi, or in some protocol that has some error, some D over F, and you want 100 bits of security, okay? And your field is not large enough, okay? And you lose some bits because of N. You can add grinding to every round of the protocol. You can add like 5, 6, 10 bits of grinding. It it really doesn't cost a lot. And then in some cases you can kind of reduce the degree of the extension field that you can get. Okay? If you take Goldilocks, you want only the second extension, you don't want to take the third one. Okay? And then maybe you have error D over F, your D may be 30, okay? You promise the client 110 bits of security, so you're kind of missing some 10, 15 bits of security. So just add 15 bits of grinding to this round, and you're fine.
Here, the e to shop is a function of delta, right?
Yep.
Okay, great, yeah. I really don't know what's confusing me about it.
So EDA, yeah, EDA is a kind of, I can't really go up to Johnson bound.
Yes,
Okay?
yeah.
This is like the optimum bound. You can get up to 1 minus the Johnson bound, minus eta.
Yeah.
Okay? And then you pay something that depends on eta. If you set eta to be 0, this error kind of becomes infinite.
Okay, the other thing that always confuses me about these, but this is sort of like obvious in some sense. Eta is less than 1, so it being on the denominator.
Eta is like 0.01.
Yeah.
That's eta.
But so I'm always thinking things on the denominator is making me smaller, but N on F is like, everything else is bigger than N on F.
In practice, I saw people kind of ignore eta. They just assume that.
That's why you should do the extra query for good luck.
But you do extra query for good luck, exactly. Yeah, okay, just do and finally, we can conjecture, but now we just, why not conjecture the same error? Okay, we kind of have the same errors in all the cases. This is the conjecture for the correlated agreement. We just have more or less the same conjecture for the mutual correlated agreement. Okay, you can actually play with the conjecture. This is a simplified version.
When grinding, how many bits can you add there? Like, is there a reason to not like push most of the security on the grinding part? Like,
so if you grind with W bits, okay, you gain W bits per that round. It means that the prover will have to work to do 2 to the W hashes, okay? But the honest prover does it once per round. So if you add like 15 bits of grinding, doing 2 to the 15 hashes on my Mac takes like 10 milliseconds or something like that, okay, about 100 milliseconds. And then you only do it once per round. So if I add 15, 15, 15, I'm not paying 2 to the 45, okay? I'm paying 3 times 2 to the 15, okay? So just do 3 times I need to solve it. So that's what it costs to the honest prover. And then you can add, every round you can add a different amount. This round you can add 3 bits of grinding. This round you can add 10 bits of grinding, like whatever you want.
it makes sense. Thank you.
This grinding is non-negligible. Is negligible only if your D is really big. So if D is small compared to
If it is small, then you take your feet can be smaller.
yes, but then if D is small, then
Okay, if D is small to begin with and your field is 128 bits, then okay,
I mean that
you're
when
fine.
when D is small, then the prover work is already small. If you add
Ah,
grinding,
yeah,
it becomes
okay.
becomes significant.
Again, depending on the application, sometimes people don't care. In some cases, maybe you just want a big server creating proofs, and he's willing to even have ASICs to do a lot of grinding. Okay, just wants to compress proofs to be smaller. Okay, maybe this is a server that kind of aggregates proofs. So he takes many proofs, and then he just want to aggregate them to one that is very small. So he doesn't mind like doing a lot of grinding, and then creating a small proof and publishing it. So depends on the application. Typically, you're right. What I do is I measure the amount of hashes the prover does already, okay, without grinding, and then I say, okay, let's add like 10%.
Yeah, you can add the same, then prover work just doubles. And
Yeah, double. I don't nobody wants to double. I add like 10-20%, and I say that's the good amount of grinding. Okay. Okay. So this is a conjecture, and this is kind of the price is to prove it. I guess any one of them, right? It's not like somebody proves the correlated agreement and not mutual. We don't give him. Okay, I guess. Just as Giacomo mentioned, like this changes the query complexity you want. So if your rate is half, okay, then the number of queries you need to do, if you're in the unique decoding, you kind of need 308 queries. This is to get 108 bits of security, okay? If you're in the 1.5 Johnson, this is the amount of query. The Johnson bound, it slightly goes down. and then capacity bound is exactly 128. Okay? Why? Because every query gives you 1 bit of security because rho is half. Okay? Up to here it's like ignoring the eta and stuff like that. Okay? If you have a small eta, then do +1. Okay, or +2 everywhere.
Well, I think it's getting worse when we go from unique decoding to 1.5 Johnson.
Yeah, I think we have it here. Okay. So, yeah, this is like a map. Giacomo, did you make this map?
Yes.
Okay, it's really nice. It tells you like which version you want to take. Okay, because it depends on the parameters, right? A third square root is sometimes worse or better than over 2. Okay, so it depends on the parameters.
Because the batching error gets
So if
worse?
you're comfortable with conjecture, you just take the capacity bound. That's always the best. If you're not comfortable with the conjecture, if you have a large field, just take the Johnson bound. If not, you check if rho is bigger than 0.23. This is kind of the threshold. Okay,
Is
if
the point-
yes, you take unique decoding. If not, you take the Johnson.
Is the point that the 1.5 Johnson bound can be worse than the unique decoding bound in some state?
Yeah.
Yeah,
Yeah.
wrong.
Exactly. Yes. This is where it's best.
I have one question.
Yeah.
What happened with the number of words?
Yeah, good. So, okay. Okay,
Good. Just a few.
so, good. So here we kind of stated this. So this is for L world, right? And we have the dependency on L, okay? Now this depends if you take, this depends kind of on your generator. If you take a 2-way random linear combination, then usually you don't start for this factor. And if you take powers of alpha, then suddenly the Schwarzschild is has degree L and not degree 1, so you kind of lose this factor of L. Okay. In these results, it's kind of this is stated for L equals 2.
Okay. This is
Okay.
for L equals 2.
This would equal 2, but I think these are the same results even for big L as long as you take a random linear combination.
Yeah.
Okay. In practice, we don't like to take random linear combinations.
It should be absorbed by the whole philosophy,
Yeah.
right?
Yeah, in practice we want like 1 alpha and then taking powers of this alpha, it's less hashes for the page and it's
But if you have many words, can't you apply the theorem like recursively splitting into 2?
so for 2-way random linear combination,
Yes.
I think that
If you
could
use-
work. I'm not sure I think, but for powers of alpha, okay, then you
These
cannot,
powers of
If
alpha.
you
if
cannot do
use-
it and then you have this factor.
If you use multilinear combinations of randomnesses, it works. Black box. Also, if you choose for every component, every word, it's separate randomness. There are black box reduction to a single 2 polynomials and 1 randomness case.
So just in this definition,
Will you have then not L but logarithm there?
I'm sorry?
I mean, with this approach, if you just split it 2, can't you have better than L here?
Yeah,
Just-
I mean, in this case, L is L minus 1 is equal to 1.
so notice
This
that
L,
in this
this L just
definition,
comes from this very specific choice of randomness.
Okay.
so notice that here we define the generator to be 1 alpha, alpha squared, up to alpha L minus 1. So that's why here we need to pick L minus 1 factor.
But anyway, the relevance that should be given to the randomness, that generator gen, is secondary, right?
Okay.
What do you mean secondary?
Like it's, like the way you randomly combine the words, it shouldn't matter.
No, every generator has a different error. The best generator is to use 2 randomness. This is kind of absurd random generator, so you additionally have some error because you use less random bits.
Okay.
Okay, you only use 1 random field element, well, instead of N random field elements. So you expect to have more error, like there's much more constraints on this.
So how do you relate this slide with the one that you had before, where there was no condition enforced on the alphas?
Yeah, so here I'm saying this is an error for gen. Every gen
for that
has an error.
okay.
Yeah, fix some gen. I say that it has mutual correlated with error if it satisfies this definition. And the conjecture is saying that for this specific gen, we have this error.
Okay, good.
Also, just if row is 1/16, then kind of every query gives me 4 bits of security, or at least almost 4 bits of security. And then when you go back to the capacity bound, look, we actually can only have 16 queries.
All of the numbers there are.
No, why 16?
I don't know.
No, this is a mistake, Jeff.
Isn't 128 by
No, it's, you divide it by 2. No, okay, so these numbers are not. No, it's not 16. It's 4 bits, 128 over 4.
Yeah, I might have fucked up.
Wait, but you divided by 2 each time.
Yeah, you divide it by 2, but you
Divide
divide it.
No, if you break it on top, then
Row is not, row is in the base.
This is 128 over 1, this is 128 over 2. This should be 128 over 3, and this should be 128 over 4. Okay? So this is 32 bits without grinding. If you do grinding, you can have like, let's say 100 over 4, which is 25 bits. Okay?
I'm sorry, I'm a theoretical guy. Numbers confuse me.
Yeah, fine. And if you only want 100 bits of security and you do 30 bits of grinding, then you only need 70 bits of security here. And then if you have rate 1/16, you need only 70 over 4 queries. Okay, which is kind of already becoming less than 20. Okay, it's small numbers.
All of the numbers there are to target 128 bits of security.
Here the numbers are supposed to have bits of security, but that's a slight.
But it's the number of samples, right?
Mm-hmm. Yeah.
But that's right.
What? No.
Capacity.
16 is not correct. 16 should be 32.
You just have enough number of samples than a Johnson, right? That's what I recall either.
But
So
the Johnson is also not correct. So
what?
it's half of the Johnson, but the Johnson is also not correct. So.
Yeah, I think
Okay.
I did my calculation were wrong.
Okay, we'll fix the slides. Okay, and then we'll resend them. I just want to finish with the last thing. Okay. So in the weird paper, we actually used the mutual correlated agreement to prove this lemma. This decoding preserves the lemma or something like that. And actually there we show that they're equivalent. So this is, if you assume the lemma is correct, the mutual agreement holds and vice versa. So what is the lemma? I'll try to, so don't look at the lemma first, let's look at the drawing. Okay, and then we go up. Okay, am I out of time?
Yeah, if you can run.
Okay, so I'll just finish this slide and that's it. Okay? So now we have this correlated agreement and this is the picture. Okay? Now what we can do is we can look at the list decoding of this word. Okay? Meaning all the code words that have some distance delta to C star. Okay? It has some list decoding and there's many code words there. Okay? So this is circle number 1. Okay? Now we can look at the list decoding of each of the CIs. Okay? Each one has a list decoding, has a circle.
In an interleaved way.
Okay. Huh?
The interleaved list.
The interleaved list. Okay. Yeah. Right. So yeah, so I'm looking at it like as a one interleaved code words. Okay? All of them. Okay. Now what the lemma says is that if you take these, you take a random linear combination, and now you do this decoding, you're going to get the same set of polynomials as if you first took the list decoding of the CIs and then did the random linear combination. Okay? So you don't expect to get something different, and this kind of, I think it's a very nice lemma that actually follows from a correlated agreement. You want to say something about this?
It's super nice, and the other way you can think about it is that if each element in the list decoding of the output is explained by an element in the list of the interleaved code. So I kind of like, one direction is obvious, like if I have like things in the left-hand side, I can move them to the right-hand side because, code words map to other code words. What's interesting is that whenever I look at something on the right-hand side, I can explain it in terms of things on the left-hand side.
Can you see it in the category theory way?
Yes, you can. Like I have it in one of my slides. It's very beautiful.
Okay. Wait, right and left, you're talking about below
This
is
line.
Right, yeah.
Okay, so kind of you start here and you can either go here or first take a random linear combination and then take a list decoding, okay, or take a list decoding and then a random linear combination and you get the same set. And yeah, Giacomo sent it, I think, nicely. If you look at the C star, you look at the list decoding, you want to kind of explain why is this polynomial close to C star. You're like, oh, there is an explanation. They say, I go to the CIs, I look at the list decoding, oh, it's there. You decompose that polynomial to things that are close to the CIs. Okay, I'm just gonna finish with that. Thanks.